Hi students, this lecture is on isotopes. In this lecture you'll learn what an isotope is, how to identify an isotope when you see it, and write the proper notation for an isotope. And lastly, to be able to compare these concepts, the isotope concept, mass number, average atomic mass, and radioactivity. Now, this is an older movie. If you've seen Spider-Man 2, this is like kind of a bit of an awkward connection here because this came out when I was like maybe a freshman in high school. But in Spider-Man 2, the Dr. Octopus is trying to achieve what's called nuclear fusion, which occurs when actually the sun takes hydrogen and fuses hydrogen together to make something called helium, which you've probably heard of. But when you put two bits of hydrogen together and make helium, an interesting thing happens. You actually get some energy out of it. And so what's happening here is actually it's science fiction, right? But it's a real process that people are trying to achieve, and they think they might have it in the next 20 years or so. Sustained fusion, basically creating like a little mini sun. That's what's actually depicted here is supposed to be that sun that he's creating, and he's using these arms to help contain it, and then the arms go crazy and start, making him evil. So that's the movie. But in reality, actually fusing hydrogen together is why the sun is hot and why we're alive. So nuclear fusion works that way. I tell you about this not because we're going to study nuclear fusion. That's actually for another course, another time. But we're going to study isotopes. And in that movie, he uses this substance called tritium. And tritium is, it's not that, but that's supposed to be the tritium in Spider-Man 2, that they buy. It's worth many billions of dollars or something. But really what is tritium? It's a version of hydrogen that weighs more than regular hydrogen, or the hydrogen we're used to. And we give it a special name. We call it tritium. So let's get into the idea of what isotopes are. Here's that tritium. It's a real thing. It just doesn't occur very often. In fact, almost never will you find it. But it is possible to make it. It just happens to be radioactive. So it's really, really hard to even get your hands on it. But isotopes are atoms of the same element that differ in the number of neutrons that they have. That's it. That's the only thing that kind of explains what an isotope is. It's just you're changing the number of neutrons. So we can see that by looking at the one on each of these. I mean, they're all hydrogen. They all have the same number of protons. And you can see in the visual, we just add a neutron here, and we add another neutron onto this one. And so they end up weighing a bit more, right? And in this case, we can just say that isotopes of an element all have the same number of protons, but they vary by mass number. And this is the right way to write the notation for an isotope. An isotope is, just identified by its atomic number. So hydrogen and the number 1 are the same thing, basically. The number 1 tells you that it's hydrogen, but the mass number on top tells us how many mass-carrying particles there are. In this case, the only mass-carrying particle is the one that it has on the bottom, the proton. There's no neutron in there to add extra mass. And this is the most common form of hydrogen that we're used to. This is the kind of hydrogen that's in water, right? H2O. And another note here is that isotopes generally have the same chemical properties to one another. So that's not a super big concept here, but it might just come to mind like, well, so is this a new element? No, it doesn't have any real different chemical properties. I mean, very slight differences, perhaps, in how it might start a reaction or continue in a reaction, but it still does generally the same thing. If you wanted to make water out of deuterium, or technically out of tritium, you could. In fact, people do it. Deuterium, or deuteriated water, is a very very common practice, I guess, if you could say it's common, for people to do and demonstrate on YouTube. I've seen probably 2 or 3 people do it just from looking around on YouTube. And this is called heavy water ice. So the heavy water ice is basically just deuterium that's bonded with oxygen, and you've made ice. But the weird thing about it is that this ice sinks. The reason is because the deuterium is actually a little heavier. It's actually heavier by 2 neutrons. There's an extra 2 neutrons in a molecule of deuteriated water compared to H2O. And that extra bit of weight actually makes this molecule, not this molecule, but this molecule, just high enough in the density to sink in water. Okay, so the way that we write this, we've already shown you. It's demonstrated here. Carbon can be written as carbon 12, or what we call carbon 14. There's also a carbon 13, by the way, but there's 2 different versions here. The way to identify these different numbers is shown right over here. So I have my chemical symbol for the element, and they're representing that by the X here. I could put anything in for that. In this case, I'm just going to put C as carbon. So the chemical symbol, and then I put the mass number, which they're calling A, and A this is maybe a little bit of a confusing equation, but Z plus N. N stands for the number of neutrons. And Z is actually a very traditional way of people saying proton number. So in this case, carbon has 6, so Z is going to be 6 in this case. And then the mass number is, as represented by A, would be Z plus N. And if I had 12 neutrons, 6 plus 6 would be 12. So carbon 12 is represented here. Carbon 14 is represented here, and then also carbon 14 is represented there as well. The reason that it's missing is to show you that sometimes chemists are lazy, and we don't always bother writing, the atomic number if you already have the chemical symbol there. So if we have the chemical symbol, it's implied that there's a 6 there. And so whatever you write there is more just identifying the isotope, and we know that the atomic number has to be 6. Okay, how do we name isotopes? The way that we do it is we use the actual chemical name, so in this case carbon, and the particular mass number, in this case, they're labeled up here, right, to name the isotope, and we'll connect it up with a dash. So this one's going to be carbon 12. That's how we name that. You can also write C, because that's the symbol for carbon, 12, like that. I told you chemists are lazy. We don't like to write things if we don't have to, and so if we already know the symbol for carbon, well, why write the word carbon? There's actually a typo with this one, so I'm going to change it on the fly here. I just changed that to 13. That exists, and I wanted to change it like that. So this one's called carbon 13 or C13. Either is fine. And then this one, which we know the 6 should be there, but we're lazy. We don't always write it. Carbon 14. So those are 3 different versions of carbon. These versions of carbon are what we call stable. And this one is what we call an unstable version. Pretty much that means that it's going to be radioactive and release radiation, and we'll actually talk a little bit more about that at the end of the lecture. So a big question you might be asking is, hey, on my periodic table I get these weird numbers. What is that number about? Because I get it, there's carbon 13, there's carbon 12, but this is neither of those. Like, why is that number a decimal? Well, first off, because of those isotopes, what we call the average atomic mass, and you'll see that written often. They call this number average atomic mass. It has to be written as a decimal because it's an average. If you think about averages, like if you're going to run a 6-minute mile, right? That'd be really fast, for me at least, to run a mile in. But let's say that's on a good day, you're running 6 minutes. But on a bad day, you're running 8 minutes. Well, what's your average mile time? Is it 7? Well, maybe you only run that average mile time maybe you only run that slow mile time like once a week, or once every 2 weeks or something. So that 8-minute mile time is going to be affecting your average. You're not going to always hit a 6-minute mile, but your average is going to be closer to 6 than it is to 8. And so that will explain a little bit. Maybe you can kind of get an indication of which version of carbon's most frequently found in the universe, or at least on planet Earth. The average value that's down here corresponds with the different isotopes that are in that element, and like I said, on planet Earth in particular. So what we mean by this excuse me, is that some isotopes are actually naturally more occurring than others, and that affects the average. So what's your regular mile time? Well, I normally get a 6-minute mile, but sometimes I run an 8-minute mile. Most often I run 6. Well, is your mile time going to be closer to 6 or closer to 8? It's going to certainly be closer to 6. So it's not going to be, it's not going to be 7. It's going to be something like maybe 6:25, right? Who knows? Like that, but that is a decimal, and we have to make it into a decimal because 6 is most often, and 8 only happens every once in a while. Well, what do you think the most common form of carbon is? Carbon-12. Carbon-12 is very, very common. In fact, about 99 out of 100 atoms that you'd find of carbon are going to be carbon-12. But carbon-13 is also out there, and it's stable. It forms, and it'll stay formed, and it won't decay or turn into anything weird. And so it will happen, but it's 1 in every 100 or so carbon atoms that you find. And so because of that, it draws that average value up just a little bit from 12. Because 12 is about the right number, but it's a little higher than that because carbon-13 weighs a little more. So it's going to draw the average up. Okay. We had mentioned that we were going to talk a little bit about radioactivity and how this kind of all connects back to that. Well, isotopes aren't always stable. There are unstable isotopes. And the types of unstable isotopes are called radioisotopes. A radioisotope is an isotope that decays or turns into something else. And as you can see, all the different colors here show the different types of radioisotopes. The stable ones are the black line. So do you see that black line in the very, very center here? Here and there. Those are all the stable ones. But the rest of them are the unstable ones. So there's a lot more unstable isotopes than there are stable isotopes. But just because that there are lots of unstable ones doesn't mean that you'll find them all over the place. In fact, because they're unstable, they will hardly ever exist. They usually exist for really just a brief period. But because they're unstable, essentially they fall apart and they decay. We'll go more into decay later in the unit, but this is the best explanation for why we have lots of different isotopes out there, and some of them behave very strangely because they are radioisotopes. I hope that's helpful, and I hope you understand the different components of isotopes now. And radioactivity.